Okay, good evening or good morning. Thank you for everyone to come to join our educational webinar organized by the CPGIS. So we are fortunate to have the Professor Heng Cai and from the Texas A&M University and today as the speaker. And Dr. Heng Cai is the assistant professor in the Department of Geography, and she received her PhD in environmental science from Louisiana State University. So she's focused on the interactions between people and environment, and also how the interactions shape social environment vulnerability and resilience to extreme disaster events and climate change. And Dr. Cai has been supported by more than 10 grants and funded by National Science Foundation, Texas A&M University, Louisiana State Grant, and a Coastal Protection and Restoration Authority. And she has published more than 40 articles and conference proceedings. So she's very productive and emerged as a young scholar. And welcome, and Professor Cai. And all right, now you can start.
Okay, thank you, Dr. Ball, for the kind introduction. So let me share my screen. Okay, can you all see my screen?
Yes.
Okay, great, wonderful.
So we can have about 40 minutes for presentation, and then we'll have some follow-up questions and answers. So everyone are welcome to submit your questions in the chat.
Okay. Yeah. Hi, everyone. Good morning, good evening, good afternoon, everyone. Thank you for the kind introduction. So to many of us, CPGIS is the family to many of us in the GI science field. So I'm very happy to see that the rapid growth of CPGIS and also the significant global impacts. And I'm very happy to be part of this educational webinar series. So from the previous 4 presenters, we have already learned a lot about the big data, how to use big data, geo AI, and also how to address the social environmental justice issues from the previous presenters. So today I want to talk about something different, but also highly relevant to the topic of GIS and natural hazards, which is about my recent work in achieving social environmental sustainability through geospatial data science. So we are facing crisis of sustainability. So I want to show you several real world examples. This is the winter storm Uri happened in Texas in February 2021. You know, Texas is a warm and hot state, but we had a very severe winter storm at that time. And this one is about the sandstorm in Beijing, which happened last month. So sandstorm caused the invisibility of the air, causing traffic safety issue, and also is a great risk for human health, and also cause very significant environmental degradation. So this video, the third video, it looks very beautiful, right? But it's not about the beautiful ocean view. It's actually the vanishing coastal lines in coastal Louisiana. And this persistent land loss crisis has been there for decades. And it is impacting the local people's life, and because they had to relocate because of the persistent land erosion issue. So here are some real world examples. So we live in an integrated social environmental system. In this system, the built environment, human component, social economic environment, and natural environment are closely connected. So we rely on the natural and built environment. The two systems offers water, air, transportation system, shelters. So also human activities are also altering both environment, natural environment, and also built environment. So because of human activities and also the industrialization process, so on one hand, this integrated social environment system are facing the threats from natural and human components. For example, the overpopulation issue and urbanization issue, and also sea level rise induced by global warming. On the other hand, our integrated social environmental system is also facing the short-term but recurrent disturbances from natural hazards such as flooding, wildlife, fire, and hurricane. So you may have heard many times about the concepts vulnerability, sustainability, and disaster resilience. But what are the concepts? What do the concepts mean? So here I want to give you a brief introduction of the definition about sustainability and disaster resilience. So according to United Nations, sustainability means to meet the needs of the present generation without compromising the ability of future generations to meet their own needs. So it's a very forward-looking concept. So for disaster resilience, it's about the ability. It's ability of a community or one system to prepare, plan for, absorb, recover, and more successfully adapt to the adverse events. So there are different variations of the two concepts, but these two are the most commonly used concepts for the two since sustainability and disaster resilience in here. So the threats from natural and human component and the disturbances from natural hazards are inevitable. So we have to face them. And resilience and sustainability are two very closely, highly linked concepts. Both of the two concepts, the ultimate goal are about achieving a healthy society, and both concepts consider the interconnectedness of social, economic, and environmental factors that finally influence the well-being of the integrated social environmental systems. And resilience is about the short-term and mid-term outcomes of communities, and sustainability is about the long-term thing. So our ultimate goal is to achieve both resilience and sustainability. So nowadays we are living in a big data era because of the availability of various sensors, such as remote sensing, social media, and also the sensor-based mobility. All this kind of data provide a new emerging opportunity for us to describe, monitoring, and also predict the human behaviors and environmental changes in near real time and also at higher resolution. So here are some examples of the data that we can leverage to describe human responses during disasters, such as the real-time power outage data from web scraping, and also the anonymized cell phone location data that track people's movement. And also we can observe disaster responses, rescue requests from social media data. So this is a geospatial data science workflow. With the enormous amount of geospatial data, we can apply a variety of methods to model, predict, and visualize our final results through spatial modeling, through GeoAI, and also many other spatial statistical methods. So the final goal is to help decision making. for different stakeholders, whether it's community stakeholders, NGOs, or government officials, so they can use the findings from geospatial modeling, prediction, and visualization to make informed decisions. So by leveraging geospatial data science, so I want to talk about 3 case studies that I recently conducted relevant to sustainability and disaster resilience. So the first study is about measuring disaster resilience. And then the second study is to assess the disaster resilience under COVID-19. And the third study is about modeling coastal sustainability, which is a long-term thing. So first, let's talk about why it is important to map disaster resilience. So this is a FEMA National Risk Index web app. So this web app visualizes the different levels of community resilience for all the counties in the US. So resilience index can help us to answer questions like which communities are more resilient than others, so we can pinpoint the areas that are at risk. And also we can identify the key indicators that lead to the geographical disparities of different resilient levels. And also resilience index is very straightforward and easy to use decision support tools. It guides the urban planning process and inform us to get more prepared for disasters. For example, during COVID-19, the US government is using the resilience index to prioritize where to have more COVID-19 test sites and where to allocate the vaccination first. So there are many government agencies trying to develop a resilience index. So like US Census, and also this one is from Institute of Public Health at University of Mizzou. So there are some inconsistencies between all the indicators, all the resilience indices. Some counties are more vulnerable in one method, but become less resilient in another web map. So this is because the agencies are using different indicators and different methods to assess disaster resilience. So there is no unified methods to assess disaster resilience. To address the issues in 2019, so I worked with my colleagues, we synthesized 174 articles related to disaster resilience, trying to extract some useful information and derive a unified model or methods for disaster resilience assessment. So here is the current simple statistics. So when we talk about disaster resilience, we need to think about disaster resilience of what to what. So here you can see that for research object, 60% of articles are talking about disaster resilience of a community. And then the disaster type, mostly 42% are talking about general disasters, which means any kind of disasters. And 23.6% of the articles are talking about coastal disasters, and 15% are talking about earthquake. So for the countries of research objects, 42% of the articles are talking about disaster resilience in the US, and then 10% of the articles are talking about the resilience issues in China. So for the geographical scale, community is the largest topic in here, which is 16%. And also the geographical scales include county level, city level, block group level, and 10% of them are talking about individual and household level. So this is a current progress. So there are many indicators being used for disaster resilience assessment. So in here, we summarized all the indicators and have derived this table with the most frequently used resilience indicators. So we can see that the category include mostly people use indicators from economic, social, institutional, infrastructural, community, that kind of dimension to indicate disaster resilience, income, employment, education, age, and previous disaster experience are the mostly used in many of the resilience assessment methods. So we also find another challenging, which is the lack of empirical validation. So you can see that only 12% of the indices have been empirically validated. So most of the time, the index is constructed using variables from different dimensions from economic, social, infrastructure, institutional, or community to construct one resilience index. So there, here I listed several popular index. So for example, the baseline resilience indicators for communities are the famous BRIC indicator resilience indexes developed by Susan Carter from University of South Carolina, and also Rural Resilience Index and Community Resilience Index. So there is a challenge in here is that we need to validate the indices. First, we need to justify why you choose these indicators and how you design the weight scheme, and also the positive or negative relationship between the indicators and the final resilience index, and also how good is this resilience index. To overcome this challenge, there are several methods that have been used. For example, we use externally available damage data, and also we people ask stakeholders for their input about how do you think this index is good or not, and also doing some survey results to see and how the reconstruction process, how the recovery process is, and also conducted longitudinal field observations. But these methods can only validate part of the component within a resilience index, and also it takes a few years to derive that index, because damage data can only become available, released by the government agencies after a few years. So to overcome the challenges, I work with my previous colleagues, Dr. Nina Lam from Louisiana State University, who is my advisor. So we modified the current framework and derived a resilience inference measurement framework. And this framework can enable empirical validation of the resilience index. And also this framework is customizable, which means that depending on what kind of resilience you are looking at, what kind of scale, geographical scales you are looking at, you can customize and choose what variables you want to use. So basically, we divided the disaster period into 3 phases: the pre-event phase, during event, and post-event periods. And in each period, we can use geospatial data to track, to indicate its threats, responses, and recovery. And by using the empirical data, we can derive resilience curves and describing each community's behavior over the 3 phases, and then construct the validated indexes. So this framework can identify resilience predictors. What are the resilience, what are the indicators from environmental or social components really matter in this particular area? And also we can have a validation accuracy to measure how good is this resilience index. And these methods can also derive inferential models that can predict the resilience index over the next time period. So we started by applying this framework to some local area to address different types of hazards. So the one on the left is about the resilience index to coastal hazards at block group level. And then the one on the right is about the community resilience at county level to the hazard type of drought. And then we move on trying to measure, develop a national resilience index by measuring the pre-disaster hazard frequencies, economic damages during the disasters, and we use population return as an indicator of post-disaster recovery. And we use publicly available data to derive the 3 dimensions for all the counties in the US from 2010 to 2020. And then we derive this validated resilience index. It's a bivariate map showing the 2 dimensions of every county. So Brazos County is the county that I'm currently living in. So we can see that this county experienced a lower level of threats, damage, but had a very good recovery. So in this case, this county will be classified as the most resilient category. So this is about the work for disaster resilience measurement. And so disasters never stop its step even under the COVID-19. And this inspired me to look at how community behaves under both natural hazards and COVID-19. So I started with the winter storm Uri in Texas that happened from February 11 to 20 in the year 2021. So as I mentioned earlier, Texas is in the southern area of the United States. So it's super warm and very hot state. So people in Texas never saw such heavy snow, and the entire state was very unprepared when that snow happened. So for about 10 days, we experienced extensive power outage. So as you can see from the figure in the middle, many counties lost power. For over 60% of the counties lost power. And then the figure on the right side is a daily snow depth and percent of power outage during the winter storm period. And we can see that we experienced a larger amount of snow and also a larger amount, higher level of power outage during that 10 days event period. So for communities, on one hand, the winter storm caused several effects. First, the lower temperature caused power outage, and the power outage caused the closure of many public service like road network, grocery stores. They were all closed because of no power. And also the transportation systems was also disrupted. So people had a significant amount of mobility reduction. And then the mobility reduction on one hand means that you cannot interact with many others. Looks like a good thing for containing COVID-19 spread. But on the other hand, it means that people who already got infected before the winter storm couldn't get the timely health care, and they couldn't get timely testing. So on the other hand, the pre-event conditions, like pre-event COVID-19 conditions and the community's social-economic conditions are also affecting the final outcomes in here, which is one is mobility and the other one is the COVID-19 health outcome. So based on the framework, we developed this data processing a workflow. So we use data from SafeGraph, COVID-19 database, socioeconomic conditions, and then the power outage data and the disaster impact data from NOAA to analyze people's behavior before, during, and after the winter storm event, trying to answer 3 questions in here. So first question is to look at how people's mobility changes under both winter storm and COVID-19 pandemic, and also identify what are the factors that shaped the geographical disparities of mobility changes during different disaster phases. And the third question is trying to see whether the winter storm event exacerbated the health outcomes of COVID-19. So here are some results we found from the analysis. So overall, you can see here, this figure shows the changes of number of visits to different destinations compared with the pre-pandemic period in Texas. So we divided the entire event to pre-winter storm. So pre-winter storm is when there was only COVID-19 that impacting people's mobility behavior. So we can see that compared with the pre-pandemic period, overall, there was 16% of mobility reduction among all the counties in Texas. And then, but during the winter storm, the overall reduction in mobility increased to 40%. And after the winter storm, when people started to come out to get food, to go back to work, so the overall mobility reduction was 12%. And we can see here is the spatial disparities of the mobility changes to different destinations during the winter storm. So blue color in here means mobility reduction, and then red color in here means increase in the stay-at-home duration period. So we can see that during the winter storm, all the counties had mobility reduction to park, to grocery and pharmacy, and also to workplace. But the stay-at-home duration increased significantly. So we conducted a series of regression analysis, try to identify during different phases of the disaster, what are the factors that shapes the geographical disparities of mobility changes. So in a pre-winter storm, when there was only COVID, we found that per capita income play a very important role in shaping people's mobility changes. We found that counties with higher per capita income tend to experience higher mobility reduction relative to the baseline, which is before the pandemic period. And also during the winter storm, during winter storm phase, we found that snow depth is a significant variable. And generally, the higher snow depths lead to higher level of mobility reduction, and also higher, which resulted in more stay-at-home time. So in a post-event period, which is the recovery phase from the winter storm, so we found that if a county had still had higher percentage of power outage, will have lower visits to grocery store and pharmacy. This is because the prolonged so for counties, we also see this from many news that some counties experienced a very high percent of power outage even after the winter storm period. And people had food insecurity issue because grocery stores and pharmacies were still closed, so they couldn't get enough food. And we also find that income is always a significant factor throughout the 3 phases. So counties with higher per capita income always have more reduction in mobility, even for before, during, and after the winter storm period. So we also want to compare. We found that in some counties, there was increased COVID-19 impacts, which means these counties experienced higher case rate, higher mortality rate after winter storm. But in some counties, the COVID-19 impacts were not increased. So we compared the two types of counties. And so we here I want to point out two findings. One is that counties with higher percent of older people experienced increased case rate and also increased mortality rate. And on the so we also find in here the counties with higher percent of customers without power during the winter storm also had increased case rate and increased mortality rate and increased case fatality rate. So this is the research results we found by analyzing natural hazards and also COVID-19 together. So the third study is about modeling the long-term sustainability of a vulnerable coast. So there is a global crisis of sustainability, which is the sea level rise and the disappearing coastline. So from the figure on the left side, you can, this is a projected, this is from a paper published on Nature Communications in 2019, a very famous paper that projected where most people are affected by rising sea levels. So in this study, they assume when there is 2-degree temperature increase for the entire world, so there will be 10 to 50 million people in China will be live underwater. And also the second highest population that will be living underwater is in the US, which is 1 to 9 million population. So on the right side, so I feel this figure is very interesting. It's a computer simulated rendering of what Shanghai city will look like if there was a 4-degree increase in the temperature. So you can see it's a simulated, but looks very real, very striking pattern to show us if we don't take any actions by the year 2100. So many cities will be live underwater. And this is a global crisis. And this is so my study area is focusing on the coastal Louisiana area, which is in the southern area, the lower Mississippi River Delta area in coastal Louisiana. So in coastal Louisiana, there was an island called Île de Jean-Charles. And this island became the first American climate refuges because this island lost 98% of its land area into the Gulf of Mexico area, the open water area, and people had no choice but to relocate to the inland area. So they had to abandon the island that they used to call home. So I was involved in a National Science Foundation funded project called Coupled Natural Human Dynamics in a Vulnerable Coastal System to look at two things. One is the land loss crisis. The other one is the land loss induced climate migration. So where, so how people when people are forced to relocate. So in this project, we develop a coupled natural human system framework. In this framework, the central component is land loss and climate migration. And there are So when we talk about model these two things, we need to consider the impacts from both natural component and also human component. So there are dynamics going on within the two separated components, but together with coastal management and the policy making and recurrent disasters and the long-term sea level rise, so we need to develop comprehensive coupled natural and human models to model the two factors. And the overall objective is to first model the coupling mechanisms. And also the second objective is to identify the influential factors and then try to simulate the future patterns under different scenarios. So first we developed models for coastal land loss. So here are two major studies addressing the coastal land loss issue in the southeast Louisiana. So on the left side, you will see this is a projected land loss based on a historical rate. If no actions taken. So this was a study conducted by USGS. So in this projection, there was no, the only factor considered is the historical loss rate. So there is no mechanism, no model being developed. On the right side, you will see the predicted land loss pattern on the three scenarios. So the three scenarios are based on three environmental factors. One is subsidence rate, the second one is storm frequency, and then the precipitations. And this was a study conducted by the Coastal Protection and Restoration Authority of Louisiana in 2017. So both models didn't consider human activities in the model and didn't have many complex mechanism being modeled. So there is a need to develop a comprehensive coupled natural human models to uncover the underlying mechanisms and provide more accurate projections. Only with reliable and accurate projections, we can make confident decisions on how to protect, how to enhance the sustainability of this coastal area. So here we collected different types of data from environmental and human activities, which are relevant to the coastal land loss issue in coastal Louisiana. And we also derived the neighborhood conditions. So in land cover land use modeling, the neighborhood effects is also very important. So we also developed several neighborhood conditions and take that variable into the final model. So this is a workflow for the modeling of coastal land loss issue. So we collected the data from the public sources and then convert all the different various types of data into unified format and unified resolution. And we try different types of regression and machine learning methods, and then we derive the predictions and also identify the significant factors. So this map in here shows the predicted land loss probability by 10% of intervals. And we also identify that random forest had the highest accuracy in terms of model accuracy and performance. And the accuracy achieved 91%. And then we also identified the most influential factors, including two human factors, which are the oil and gas well density, and also the distance to urban area. And we also identified 4 significant factors leading to coastal land loss, including land fragmentation, distance to open water, elevation, and subsidence rate. So because of the land loss, people are forced to relocate, but there is no model for climate migration modeling in coastal Louisiana area. And there are also some challenges in here. So the first challenge is that the relationships are very complex and nonlinear and uncertain. So given our prior knowledge, it's very hard to say which factors are more important and which factors are irrelevant. And if we want to make the modeling process to make our models more effective and useful for decision makers, so we need to simulate the migration patterns on the different scenarios. So to overcome the challenges, we developed another comprehensive model. In this model, we use the Bayesian network models because Bayesian network visualize the relationships in a graphic format, which is very easy to understand for decision makers and government officials. And we use an optimization method to optimize the final Bayesian network models. And by using the Bayesian inference, we simulated the population migration on the different scenarios. So in here, we designed 5 scenarios. So the 5 scenarios include reducing hazard threats, reducing property damages, and reducing both threats and damages. And the other 2 types of scenarios are about the policies we may take, which is one is to increase the employment rate, the other one is to increase our housing quality. So this is a current spatial pattern of population change. You can see that in the southernmost area, which is close to the open water of Gulf of Mexico, there was almost 100% of population loss because the severe land loss issue in that area. So if we reduce the threats, we can see that there was a significant level of reduce in population loss. So more communities will be able to retain its population. If we reduce the damage, you can see that this we can achieve the similar pattern. One ideally, if we can reduce both threats and damage, we can see that most of the communities in southern Louisiana can have very stable population growth other than population loss. And this tells us that the sea level rise and also coastal hazards are indeed the real threat to the sustainability of this vulnerable coast. If we reduce, if we increase employment rate, which means that we offer more positions, we offer more jobs to the local people, we can see that it's still impossible to reduce the population loss in the southern area. And if we if we enhance the housing quality, the same pattern still remain, which means that for the southernmost area where the severe land loss is occurring, the only way to make it sustainable is trying to reduce threats and reduce damages, which is kind of hard to achieve. So this is the study that I conducted about modeling the coastal sustainability. So at the end, I want to say that geospatial data science has power, so we can definitely achieve more by applying geospatial data science to make our society more resilient and more sustainable when facing the future disasters and trying to make our future more sustainable. And I also want to take this opportunity to thank the funding agencies for their support. And also I want to thank my long-term collaborators from Louisiana State University, University of South Florida, and Texas A&M University. And also I'm in the process of building my own research team. So if you know someone who are interested in pursuing graduate degrees, pursuing a graduate degree in geography and doing geospatial data science in addressing the social environmental issues, so welcome to join us. Thank you.
All right, thank you, Professor Cai. And so now it's time for questions and answers.
Yeah, I saw a question in the chat box.
Okay, yeah, here is some questions I summarized here. The first, how to decide the weight for the different factors of the resilience indicators.
Mm-hmm. Okay, so yeah, we talk about the challenging of deciding the weight scheme. So previously in many studies, when they construct the resilience index, they either use equal weights or use weights from principal component analysis, this kind of statistical analysis, which has a higher level of uncertainty. So in the resilience inference measurement framework, we try to develop the resilience index from the other way around. So we started with the empirical data, and then we use empirical data to describe communities' behavior pre, during, and after disasters. And then we construct the empirically based resilience index. And then we try to model the relationships between the empirically based resilience index to the final to all kinds of resilience predictors, which are the indicators from different dimensions, social, environmental, and also the infrastructure, that kind of dimensions. And then by you can use regression analysis. So most of the time we use regression analysis. So there is no weights. There are no weights being developed in RIM framework. It's just the relationships. So in this way, we can try not to decide the weight, but we derive the empirically validated relationships between the resilience index and the resilience indicators from different dimensions.
Okay. Yeah, this is okay. There's many the way in statistics how to decide the ways. You can use expert survey or use the principal analysis. Yeah. Okay. Professor Gao Sheng, you have questions?
Yeah, Dr. Brown. Yeah. First of all, yeah, thank you very much. Yeah, Dr. Cai, for your wonderful talk, very inspiring. And then I'm interested in your second study, especially I'm wondering because when you analyze like the impacts because of the COVID-19 as well as winter storm, so that's a two maybe natural or human caused disturbances events. And you analyze some of their differences or changes. So because those maybe impacts or shocks are happening simultaneously. So I wonder, when you analyze them, maybe together or separately, how can you, differentiate maybe one difference from another? Or, this is a very, in economics, they call the difference in differences. I wonder, so in this case, it's, how can you know, okay, this changes is caused by one versus the other? Yeah, this is very interesting.
Yeah, that's a very good question. So divided. So first, I divided the research, the event into three phases: pre-winter storm, during winter storm, and after winter storm. So each phase had 10 days. So for the pre-winter storm time, that 10 days, and so we consider the mobility reduction was only affected by COVID-19 because winter storm had not happened yet. And then we compare the during winter storm period. So the during winter storm period had both COVID-19 impacts and winter storm, and then 10 days after winter storm period, which was when people start recovering from the impacts of winter storm, and because people can go outside. And so we divided the entire period into three phases. And we also compare, for each phase, we developed a series of regression analysis and try to see what are the factors in each event period. The factors are different.
Yeah. When you do the the regression, I wonder whether, because this is more like two treatments, whether you consider you control yearly, for example, for the same before and after winter storms, you also consider maybe year in 2021 and also year 2020, as well as maybe year in 2019, for the same, before, during, and after winter storm.
Mm-hmm. Yeah, that's also a very good question. So the winter storm was about 10 days. So so we didn't look at the 1 year period because its impact in terms of mobility reduction was about 10 days to 2 weeks. So after 2 weeks, after 10 days, people's life almost returned to normal in terms of mobility. But in terms of economic impacts, in terms of recovery, like the housing reconstruction and housing, the power grid was restored in 1 week. So if we look at the long-term effects of the winter storm, we may look at the year before, winter storm, the year during winter storm, and the year after winter storm. Yeah, but regarding mobility, we only look at 10 days.
Yeah, makes sense. Okay, yeah, I will chat with you more after offline. Yeah, thank you very much.
Thank you.
Okay, maybe here is another question. Does the resilience, what do you have in those research, mostly is for resilience to environmental disaster? And do we have the different measurement of the resilience, say that's to natural, social, economic, political shocks?
Mm-hmm.
There might be a difference, right?
Yeah, so for different types of disasters, whether it's public health, such as COVID-19 or natural hazards, so the indicators we use can be different. Right. Yes, so but the overall workflow, the overall framework is could be modified to fit different purposes. Yeah, so for different types of emergencies or disasters, we can change the indicators, and we can change we can modify the methods to address different challenges. So
the resilience might be basically too general the concept, and the probably only resilience to some the shocks, not to all the shocks. Also, the different measurement of the resilience will be and a target for different shocks, right? Yeah, okay. And does any make difference for resilience in the short run or long run? How you make the difference?
Yeah, that's also a very good question. So resilience is resilience and sustainability, they are very broad concept. So in different disciplines, people view resilience differently. So for people in civil engineering and in geography, in environmental science, we have different views of the concepts. And different views of the concepts lead to different methods, different approaches to address that concept. And so so when I talk about the concepts of resilience and sustainability, sustainability is about the long-term, cross-generational things, not only for one week, 1 month, or 1 year, it's about decades. But when we talk about resilience, it's about short-term and also medium term. Medium term can be 10 years, 20 years, but if you get longer, that will be within the concept of sustainability. And when we talk about resilience, we always need to be aware of resilience of what to what. So this is very important. So in my study, the concept is resilience of one county to coastal hazards, or resilience of one block group to drought. And so resilience can also be used to talk about resilience of an individual to COVID-19. If that person is vulnerable or have a mental health issue, so he or she may not be resilient to COVID-19. So depending on resilience of what to what, we need to be more careful about the methods and the variables we are going to use.
Classification, right?
Yes.
So you need a classification of the. Okay, here's a question. And could you provide more detailed information about how to define the resilience index in your research? And for example, how to consider each indicators and the validation process, and which publication can I find to get more information?
Okay, how to define the resilience index, and for example, how to consider each indicator. Yeah, so in the talk, because of the time limit, I only talk about the framework, but I do have 2 papers on the specific methods we use, and the specific data mining and regression analysis we use to classify the to calculate the resilience index. So I can provide the paper in here so that you can search on you can find the papers.
Okay, here's another follow-up questions and regarding the user regression. And I just wonder what type of regression analysis have you used?
Yeah. So sorry, I didn't mention that in the talk. So for the winter storm study we conducted, we used a GWR, geographical weighted regression in that part.
Okay. Well, okay, so if you use the GWR, so that means the scale of the resilience measurement where should make difference, right? Is the scale is by the neighborhood or by the township, by county, or by state? That might make difference, right?
Yes, definitely. That's a very good point. And so in this study we conducted at county level, and we try to gather more data at finer scale and look at more finer geographical scales. That's the ongoing work in my research team. And,
okay, could you specify why you pick up the county level?
So first, this event, winter storm, affected the entire affected all the counties in Texas. So that's the first reason we want to look at the entire Texas. And the second reason is that for many so power outage was a major impact, a major factor for causing all the disruptions in public service, in mobility reduction. And we can only get the power outage data at county level. But right now I'm working with my collaborator from University of South Florida on deriving finer scale power outage data from nighttime images. So once we get part of work done, we definitely will conduct research at more finer geographical scales, for such as block group level or neighborhood level. So hopefully in that time, we can compare the studies at two geographical scales to see what are the differences. That would be a very interesting study.
Okay. And another question with me, what software for your linear analysis, and how about replicability?
Okay, yeah, so we didn't use any specific software. We use programming, a language.
Python?
Yeah, Python or R is statistical analysis. But you can also, if you want to use some commercial statistical software, is also you can also do that.
Okay, so does your program shareable with others?
For now, we didn't make it publicly available. But if more people are interested, I would be more than happy to share that.
Okay. Is there any other questions? If you maybe you can also turn on your microphone if you'd like to speak. Okay, and if there is no other question, maybe this is a final question. And in your resilience, does the social structure or like some social organization or economic structure, like some industrial structure, and make a difference in resilience? I didn't see this one in your measurement, because for one county, if all the county say one industry, right, or one business, or all in tourist business, and they can make huge difference.
Yes, that's a very good point, Dr. Ball. So resilience is when we talk about decision making, when we talk about management, we need to identify for every study, we need to know who are the stakeholders, who are the decision makers. So in many studies for constructing resilience index, they have some kind of qualitative variables indicating, the institutional factors, governmental factors. If you have that qualitative data available, and you can definitely incorporate that qualitative data into the modeling process. So for my study, most of the data were geospatial data, and collected by either publicly available data sets or from the purchased, or from social media data or human mobility data. So for now, I haven't considered about incorporating the institutional factors into my modeling process, but it is very possible to incorporate that data into the modeling process, as long as we have that data available. Even that data is qualitative or categorical, it is still possible to incorporate that into the modeling process.
Excellent.
Thank you for that question.
Do we have any other questions? Actually, from the one data, this economic or social structure, you can get from the business survey. They have how many the different kind of classification of the firm of the business. Those data actually are on the public domain by the counties.
Okay.
Say how many the firm production, how many on sales, how many on different kind of business. Yeah.
Okay, that's good to know. Thank you.
Yeah. Okay. Okay. And if there is no more questions, now it's good time, and now it's almost just more than 10 o'clock. So thank you very much. And we'll have the recording for this webinar, and we'll share this recording after this webinar. And thank you very, very much. Also, thanks to every participant. Or Dr. Wu, do we have any announcement?
No, we have the next one is next week, the last webinar for this series. So looking forward to seeing everyone, and thank you for attending, and thank you Dr. Bao for moderating, and also Dr. Cai for giving the awesome webinar. Thank you, everyone. Take
All
care.
right, thank you.
See you
Thank you.
next week.
Have a good night.
Mhm.
See you
Time
next